Hello. Thanks for joining us today at the Charge Virtual Conference on EV Engineering. I'm Christopher Rolfe, the publisher of Charged. The topic of this session is inverters on a plane, testing of electric powertrain from prototype development to certification and systems, and it's brought to you by HBK. There will be a Q&A session after the presentation, so please click the Q&A button on your screen to submit questions at any time. And without further ado, please welcome our speaker, Mitch Marks, Head of Business Development, APAC Electrification. Welcome, Mitch.
Thanks, Chris. And I think I run with it from here. So thank you, everyone, for joining. Looks like we got a good number of people rolling in. So this session is inverters on a plane, testing electric powertrain from prototype development to certification and systems. It really inspired by a movie. So I'm testing these motor flying inverters on this motor flying plane. And it'll hopefully be a good overview of some of the testing HBK has been doing with electric aircraft, more electric aircraft, and some of the eVTOLs. For those of you who don't know, HBK is a test and measurement conglomerate where we're really looking at helping R&D labs to understand the products they're developing. So without further ado, inverters on a plane. There will be no Samuel Jackson. All right, quick overview. So we're going to do an introduction to HBK, just a little bit of who we are and what we do with electric aircraft. Challenges in more electric aircraft testing. And then I'm going to go over a whole bunch of different testing types, system level test, performance, high phase counts, and get into some interesting stuff like structural flutter and how electrical systems can have a big impact on things like mechanical structures. So let's get into it. This should be fun. So a little intro to HBK. As I mentioned, HBK does test and measurement in a wide variety of applications. Today we're going to be focusing on power quality and fault testing with electric systems, as well as electric powertrain development. But some of the other areas of HBK are structural durability and fatigue testing, ground vibration testing, production tests for propulsion systems, acoustics, which is a really interesting area if you dig into it, flight controller validation, fleet maintenance, and HUMS, which is sensors embedded into the vehicle. So again, we're going to be focusing on the electric, given that this is charged EV. But if you're interested in these other topics, again, somebody from HBK would be really happy to speak with you. So what does HBK offer into the electrification space? I'm not going to kill you with a data sheet. I just figured you should know kind of what our background is. So we have a data acquisition system that comes in different sizes, and in these chassis, we can fit up to 51 power measurement channels. And in this electric aerospace realm, this is really relevant, and we'll see some examples of meeting these really high channel counts. We can store data for very continuous periods of time. So if you want to do a full flight sequence, understand fault injections, you have all of the data to do that. We can store as long as you have hard drive space. We can support, this is actually wrong, up to 12 torque transducers and go higher in our standard portfolio. As far as measurement, we can do voltages up to 1500 volts. 2 megasamples per second, really high accuracy on electric power. So if you're a control engineer making those small changes, or you're somebody who really needs to crunch the measurement uncertainty, we will be a best friend for you. And my favorite feature is our measurement cards, where we bring in the high voltages, have a digital signal processor on board. So we have a real-time computer where we're actually doing all of our calculations in discrete time, which allows us to feed back to things like hardware in the loop. We'll look at that a little bit. Allows us to feed back to automation systems for really fast testing. And it also, especially when you're at these really high channel counts, takes the burden off of a PC or your post-process software to do a lot of these calculations. When you're sampling at a really high sample rate, you need to do a lot of math. That can burden a PC or a data number crunching engine. We're doing that on each card. The more cards you have, the more measurements you have, the more computing power you have. So this should make your life easier from the computational process side. HBK also makes torque transducers and current sensors. Again, high accuracy, high bandwidth, and our measurement system does support a wide variety of other measurements like microphones, accelerometers, temperatures, CAN bus. And what we'll see is in these electric aircraft, this is very much an electromechanical system. So you really need to understand that battery to propeller type operation. So that's what we offer. We do have a new product, which we're pretty excited about. This will be releasing at, November. It's coming up quick. We call this our satellite or our fiber optic probe based measurement system. You have a little box that sits right next to the measurement. We digitize it and we send it back to the measurement unit over fiber optic. This will be up to 2000 volts, up to 20 megasamples per second. If you really want to get into the hairy details on some of those inverter behaviors. And again, that same really high accuracy. And what that looks like in practice is you'll have your little box sitting right next to the measurement. You'll have super short measurement cables, so you're not picking up EMC, you're not picking up electric noise on your measurement. You'll have a current box that sits right next to your current sensors. It'll power those current sensors. And again, really short cables, you're minimizing your exposure for EMC. That measurement is then fiber optic. So it's completely safe, really, really the safest measurement you can get, which is going to result in a super high quality. We're extremely excited about this. This was really made for the aerospace industry. Uncompromised safety, because you don't have high voltages getting back to the measurement unit. It's not getting back to people. It's not getting back to computers. The short cables are effectively eliminating a lot of EMC issues, and we'll talk about some of those issues in a moment. High accuracy for some measurement nerd stuff. We're going to have fewer reflections, so an available higher accuracy. Integrated power supplies, and if you're doing full aircraft, these things can be distributed up to 500 meters, so the measurements don't need to be near each other. So this is exciting, and we're going to see this a couple times throughout the presentation as well. So at the end of the day, what we're really good at, and I'll get to the good stuff in a moment, is measuring electric and mechanical signals in one place. You can look at your inverter voltages, currents, torque, speeds, accelerometers, microphones, all in one place. We make really fast and accurate efficiency measurements for doing things like flight cycles. We can expand to really high channel counts, so you're effectively future-proof. If today you need 20 channels, but tomorrow you need 50, we can help expand with you. We record data and give a scope functionality. If you're in that prototyping troubleshooting phase, you have that recorded data. You can see that data live. And if you need certification, if you need post-processing, you have all of that data as a transparent reference. And again, we do all of our calculations in the real time, so you can have them for real-time feedback. So we do sensors, we do data acquisition, we do software, and in most markets, we have local support and training. And this presentation will feature examples using these products. All right, so I'm giving this a try. We're going to do poll question 1. So Chris, if you could put up poll question 1, that would be greatly appreciated. Oh, I get it too. So yeah, the question is, do you work in electric aircraft? I know a lot of this market is for automotive, but I think this will equally be as of interest. And one of the things we're seeing is a lot of people who are in the automotive space starting to move over to some of these electric aircraft companies are showing interest because at least on the electric powertrain side, the skill sets are quite overlapping.
All right, looks like we have a few people still entering the answers here, so I'll give it one more minute.
Cool.
One more moment, rather. All right, here we go. Poll results shared.
Oh, cool. All right. So we got a lot of people interested. We have a good number of people in the aerospace world and only a few automotive. So that's great. Thank you guys. And a handful of people who are expecting Sam Jackson. So I'm glad the joke wasn't lost on everyone. All right. So HBK's history with aircraft electrical systems. How did we get into this? So at the aircraft level, HBK has actually been involved in measuring electrical networks for quite a while. So in the aircraft, we'd be measuring the full electrical system, looking at power quality, looking at fault simulation. This is hundreds of channels. In some of these airframers, there will basically be the aircraft electrical network sitting in a room where they go through different flight sequences and they make measurements on all of these points for an extended period of time. And they're looking at actual APUs, starter generators, cabin compressors, and in the more electric aircraft world, um, inverters, power distribution, and some of the batteries even. So HBK has a long history in aircraft electrical testing. So that's how we got into this, was really looking at that certification level measurement of high channel counts, to understand problems happening in the aircraft. And we like to think we're continuing that. So what do some of these tests actually look like? Well, you'll have various components located all over the aircraft. Actuators, starter generators. As the aircraft becomes more electric, we're seeing more and more of these things. So we'd have measurements at each one of these points, looking at that power distribution throughout the aircraft. Sorry, fumbled with the keys there. And what a lot of this is equating to is doing harmonic analysis, where they're recording the data for the power quality. They're looking at the quality of that sine wave, and this is one of the things that is going back to certification. We're looking at to see, is this aircraft safe? Can we trust this electrical network? And this is just a screenshot from our software showing some of that harmonic analysis that's available. So if you're still doing some of this traditional work, and this certainly is not going anywhere with these new aircrafts, this is a feature we can offer for years now, where we really bin out those harmonics. But let's stop lingering on the boring stuff. This is actually quite exciting, and get into some of the new things. So what are the challenges in electric aircraft testing? And I think my boss is on the line, so I hope I don't get in trouble. These mother bleeping inverters on this mother bleeping plane. Well, now that we have more and more of these inverters, more and more of these motors on the aircraft, the whole power quality becomes quite an issue. We're seeing lots and lots of test points, more than we previously had. We're going from maybe 1 or 200 to several hundred, and people are doing this on the full aircraft. So this really needs to be distributed in size. We're also seeing new requirements, more power channels, more voltage channels, and this is really looking at those EMC issues and harmonics, because we have our traditional aviation buses, but with these higher voltages, with these higher switching frequencies, EMC is becoming a really big issue with getting these aircraft certified and safe. In the more electric aircraft world, we're seeing voltages push up to that 3 to 5 kV range. And most of you probably know that has a real issue with partial discharge, a real issue with electrical noise. So this is a huge challenge, not only for the aircraft, but also for the safety of testing. Higher phase count motors, just leading to more channels, physically larger setups. Traceability is a must for certification. And unfortunately, a lot of these certification things are still evolving. So these are the challenges we're facing. Now, how do we approach this? Well, this comes back to that satellite product we have coming out. We would put a satellite at each one of these locations within the aircraft. These can be distributed throughout, up to 500 meters. We would then have our measurement systems potentially distributed, connected to these fiber optic probes. So those measurements are very safe, and we bring in those high voltages, very noise immune level, and we can bring that back to the PC, one storage location, one data file, one viewing, one line of traceability. So HBK is definitely still doing work in this area, and with the evolution of it, we find it quite exciting for really making the measurement easier, making the measurement a higher quality, and giving you some sanity with the data chaos. So we find this quite fun. Now, what are the major concerns with some of these new novel aircrafts? You know, it's weight and range, and I think those are almost interchangeable, and safety. So what are we seeing on kind of the eVTOL front? What are the snakes in that plane? Well, in terms of testing complexity, many motors. You know, the NASA X-57 kind of famously has their 14 motors. We don't see we see numbers between the 5 and much higher level. Higher voltages. Some of these are floating around 800 volts, but that is still quite high and creeping higher. The inverter-driven nature, we're pushing these higher switching frequencies, we're pushing these phase counts, we're creating a lot of that EMC, that noise that can get to avionics, that can get to all different functions of the aircraft. And then in terms of integration complexity, these are a little more technical, but for the weight purposes, there's a lot of lightweight motors, which means they're low inductance, which means they have current ripple, which means we have a lot of torsional vibration or torque ripple happening at the shaft. These torsional vibrations cause bending moments in propellers, so that electrical system has a direct effect on that mechanical system. We also often have this, 14 or 12 or however many motors plus actuators pulling on either one or two DC networks. We're pushing a lot of this harmonic content onto that DC bus. That is a power quality nightmare in and of itself for certification, for stability, for the safety of the aircraft, and then the traditional power quality as well. So there's a lot of challenges introduced by just having more and more inverters, high stress DC networks, and the fact that these are just novel structures. All right, I think this is the only equation I have in the presentation, and this is some measurement nerd stuff, but I think this is really important. So on the right-hand side is kind of our traditional equation for current in terms of capacitance. But in the measurement world, this is the equation for electrical noise coupled to a signal line. So we have current equals capacitance times the change in voltage over the change in time. What does this mean? Well, battery voltages are increasing. So when this inverter switches on, that change in voltage is increasing. So that V increases, we have a higher dV. We also have high voltage safety, higher measurement ranges needed for the amplifiers, these types of things. We're seeing a push to silicon carbide and gallium nitride. We want faster switching frequencies because our inductances are lower, so we avoid some of those current ripples. Well, if we look at SiC and GaN, the real benefit to those is that they turn on and off extremely quickly. By this switch physically turning on faster, we're lowering our DT. So we have a raised DT, we have a lower DT, or a higher DT. So we're creating electrical noise. Something I don't have on here is the capacitance. But if we look at those measurement cables, the longer they get, the more capacitance they have. And if you throw a loop in there, you're also introducing inductances and capacitances. So that capacitance is also increasing if you have an increased length of cable. And basically what we end up with is higher V, lower T, increased noise. And this is really the justification for those fiber optic satellites we proposed. So these new powertrains are quite difficult to measure. From a measurement standpoint, they are a headache. And it doesn't help that I'm sure none of you have ever had a lab that looks like this, where we have loops of cable everywhere, high voltages going to various places. So these are the measurement challenges we're facing. Please don't do this. If your lab looks like this, call me. I will certainly come and help. But this is a lot of EMC. This is a lot of measurement error. And when we're developing these new powertrains, when we're trying to hunt these ghosts, when we're trying to solve problems, this is a big source of headache. So in summary, lots of measurements, electromechanical systems, high voltages, EMC, harmonic content, data for certification, and you know, it's a new industry. There's just a standing lack of knowledge, and the standards are evolving. All right. So kind of my conclusion here is that the system level really needs to be considered. You know, if we look at this inverter, it's switching, you know, somewhere probably in the 10 to 30 kilohertz range. We have these voltages turning on and off very quickly, creating that EMC. This is going to the motor. The motor windings are filtering that current probably somewhere in the 0 to 2 kilohertz range fundamental. And that current is far from perfect, largely because of those low inductance machines. You know, this is filtering that current to a torque and speed, somewhere in the 0 to 5K RPM range, most likely, but that has a torque ripple on it. And this torque ripple, those radial forces are creating noise, vibration, and potential flutter modes. But the cool thing is that inverter has a controller on board, that motor controller, where we can actually affect what the output of that sine wave is. We can affect that noise and vibration. We can affect that torque ripple. But this motor controller is going to affect these structures with vibration. And when we start thinking about having multiple motors on wings, we can potentially create you know, structural modes in those wings. So we do have to approach this as system type thinking. What we do in the inverter, what we do in the machine is not in a vacuum. It's also affecting the mechanical system. I do have a good example of this towards the end of the presentation, so please hang along. System level test, you know, we're also putting a lot of stress on that DC network. We have the inverters for the propulsion, the inverters for the actuators, and the power grid within the vehicle. So we have many draws on these DC that affect that system stability. So talking about system stability, let's get into some of the applications that HBK has been working on. So system stability and what we're referring to as copper bird testing. So in these multi-rotor aircraft, you know, the safety is really critical. There are many powertrain configurations. The certification for a lot of these eVTOLs and e-aircraft is evolving. And there's a lot of different fault conditions that need to be examined. When we're going from vertical flight to forward flight, what happens if we lose a motor? What happens if we hit a bird? What if there's a westbound wind in the rain? What if there's a lost motor? Transition states. We need to account for all of these things. And fault conditions are often difficult and dangerous and really hard to repeat in an actual vehicle. You know, how do you repeat wind conditions? How do you repeat bird strike, loss of motor, multiple rotor configurations? You know, one of the large eVTOL companies recently had a crash because they were testing their fault conditions. You know, that's just expensive when you only have a couple of structures, a couple of aircraft in your portfolio. And propeller tests are kind of the more traditional iron bird are difficult. If you don't have a very expensive wind tunnel, or a wind tunnel that you can use with transition, you do need to be concerned about prop wash and completely affecting your test. So how do you combat this? How do you do this multi-rotor, you know, fault condition testing? How do we test losing a rotor? Unfortunately, none of the companies we do this with will let me share names or pictures, so I have animations. I apologize. What we have is somebody's taking their aircraft and they're translating that to 1 dynamometer per rotor. And they have simulated propellers on those dynamometers where they're simulating the different flight conditions. There's a computer, you know, a real-time computer, hardware in the loop, if you may, that's orchestrating those simulated propellers and also orchestrating the flight controls. So they're simulating the flight controls and telling the actual aircraft motors under test how to perform. So we're mapping that powertrain to dynamometers with real-time simulation of the system in a hardware in the loop configuration. This is really cool because we now enter a space where we can be repeatable. We can do these tests confidently. Dynamometers can accurately simulate a lot of propeller dynamics. We can simulate many different flight and fault conditions and do it repeatably and predictably. It's safe. We're not losing an aircraft. And we're looking at a point where this is very seriously going to be used for certification. And probably most importantly, we're getting realistic dynamics because we're avoiding that prop wash or really expensive wind tunnels. What's HBK's solution for this? Well, we actually have quite a few of the parts. We have a division called Concurrent Real Time. They make real time computers for doing that flight simulation. This is kind of their wheelhouse for testing flight controllers. We have our eDrive system, that high channel count measurement unit, where we can record the data at a high frequency. And we can also record things like the CAN bus data, the vibration data, the electrical data, all in one place. So you can monitor your CAN bus for faults and see how your motor's performed. We sell torque and current sensors, so you can really accurately understand the torque dynamics on the propeller. And we do have a number of partnerships with test stand integrators. The benefits we deliver are really a full service power hardware in the loop, real-time computing, and data acquisition. We have that closed loop. You can certify and troubleshoot with the stored data. You simplify your test by having a single measurement system, and we really are the highest accuracy. And you can view all of those motors, all of those simulations in one single workstation. So it's pretty cool. This is one of the really exciting tests we've been working on, and if you're a eVTOL company, I would seriously consider this for looking at your powertrain stability, so your DC network stability and your flight controller stability. And the types of tests people are doing with this, I mean, they're monitoring the power flow through flight sequences. They're looking at the motor control during faults. They're doing that traditional PQ. And a lot of it is looking at the CAN network and how the CAN network is responding to fault injection. So another one of the areas, and this is kind of the traditional area we work in with both aerospace and automotive, is performance testing. So when we look at like the powertrain development, now we're zooming in on the motor and inverter. We went from system to subsystem. We have this prototype phase where we don't need that many tests and we don't need that much time, but we really are doing debug. We're looking to do the motor inverter work. We're looking at data. We're trying things. We're retrying things. We're just getting things spinning because very often these are new motors with new inverters. We're refining prototypes. That's kind of the next phase. Once things are working, we refine the prototype. This takes a little more time. It takes more tests. Now we're correlating to simulation. We're taking that data in our simulation and comparing them. We're doing lower frequency data storage, but we now need to store data because we need to start to understand the motor system better. And once we get closer to production, this is where we're refining. We have lots of tests and lots of time. Multi-physics simulation, we need high frequency data. We're doing calibration. We're looking at those different fault conditions and how we handle them. We're starting to consider certification, and we're optimizing that efficiency. So, these are the tests we're seeing for that powertrain development. And there's snakes everywhere. And what these tests generally look like, and I'm sure most of you probably know this, is we have our power source with our DC. We're measuring that DC. We have that high frequency inverter with all its lovely EMC, and we're measuring that into one common location. We're also measuring the motor torque and speed, as well as vibration and sometimes acoustics. Throw in a whole bunch of temperatures. This is a super temperature dependent system, CAN bus network, and we also do measure some other networks. We're currently investigating a lot of the new upcoming aerospace buses, and we're coordinating all of that in one location, giving you one visualization. And what a lot of our customers end up with is, whether it's a multi-phase machine or not, they have a dynamometer, they have a torque sensor, and they're making those measurements. They're often doing efficiency mapping, where they're fixing many points, measuring some data, and recording that really accurate power and efficiency measurement. And we're looking at different combinations of temperatures battery states of charge, and controls, so we can understand how to control our motor when it's hot, when it's cold, when the battery's at low state of charge. We're evaluating the mechanical performance, so we characterize the efficiency of the motor and its behavior in different states. We evaluate the mechanical performance for vibration, thermal. We execute fault analysis to see how we handle riding through faults. You know, in the aerospace, we have a lot of redundancy. We don't want single point failures. So we often want to see how can we ride through faults, or how can we predict faults. And then there's a lot of advanced analysis looking at the flux profile, the DQ0, you know, torque ripple, and again, harmonics and power quality. Now we're really good at this. We use an algorithm called cycle detect, where we can actually track the fundamental frequency and give a calculation of power factor, all of that, every half electrical cycle. We do this in our digital signal processor, so this is all happening real time. And this allows us to test extremely quickly and also accurately measure power and power losses in scenarios like flight sequences, where you have startups, where you might have bird strikes, these types of scenarios. And this allows us to efficiency map very quickly. If efficiency is your concern, if cutting weight or heat is your concern, this is a scenario where we were measuring electrical power every 1.5 seconds. Basically this is a test where we fix torque and we step through speed, and every one of these yellow or orange, pink spikes is a change in speed. And about every second and a half, we're making a very stable measurement. This allows you to go through your efficiency map extremely quickly, log those results to a table, and we can also plot efficiency maps live. We don't have any settling time, so you can really measure as fast as your dyno can change speeds. Or if you want to measure through a flight sequence, we can measure power through a full flight sequence. By moving faster, you spend less time with the machine heating up or cooling down. And again, we're going to plot these efficiency maps live. So we allow you to test very quickly. This cycle detect, and this is more of a unique aerospace thing, allows us to very accurately measure power for high fundamental frequencies. A lot of times we're pushing the machines very quickly. We're operating at, a 800, a 1 kilohertz, a 2 kilohertz fundamental. And where many tools that measure power were intended for the grid, 50, 60 hertz, our cycle detect algorithm allows us to measure electrical power very accurately, even at high speed. We can measure fundamentals in the kilohertz range, track power accurately, even if the fundamental is shifting. And if we look at an example of our calibration sheet, we actually offer calibration up to 5 kilohertz with every card, because we realize our customers are going through a wide variety of frequencies. And our measurement uncertainty is actually extremely good at those high fundamentals when you look at the marketplace. So the cycle detect, I think, is really key for being very accurate at the high fundamental. So if you have a high pole count motor, you have a high phase count motor, there's a very good chance you are going to a high fundamental and need to consider your accuracy on electrical power. Speaking of high phase count motors, here's an example of a customer we have that's doing a significantly high phase count motor. I won't give an exact number, but it is greater than 15. And we have a wide variety of measurement chassis for handling this type of measurement, because now we're looking at a space where, traditional instruments, you might need 2 or 3 of them to measure this, plus scopes, plus data recorders. And again, we're simplifying that test setup by bringing all of these measurements into one place. And what their measurement setup looks like, they actually have 2 of our systems daisy chained together. They don't always need to use both at the same time, so they have 2 of them. And they can connect them together, view all of that data in one location, make all of those measurements, electric and mechanical, in one location, and characterize their motor from prototype to production. We also have a nice tool in our software for looking at these higher phase count systems. So So here on the right-hand side is an example of our software setup. Now, this is not a high phase count machine. This is a 4-motor quadcopter, but we can measure the output of the DC bus. We have a nice little display where you can see the power from the battery. You can split this up into as many inverters as you have. So in this instance, there's 4 inverters. You can see the power offered from each inverter. And then if you have the torque and speed measurement, you can also look at the torque and speed and have a really nice graphical display of how your powertrain is operating, even during flight sequences, even as the power is shifting, even as we're looking at different control techniques. So in this test, we instrumented the DC bus, inverter outputs, torque and speed, and I think they even have a thrust measurement. They went through a load profile. They're actually looking at what happens if we try to take off with one motor down. So they're measuring the battery, voltage, and current. These are the RMS values over a 20-second flight sequence. And then looking at the voltage and current from each motor as it's trying to take off with only three of its rotors. So looking at that control technique. Recording data the whole time so we can go back and review what that flight sequence looked like, record for potentially minutes or hours, do that power quality analysis, and also look at behavior during faults. So this is a really nice feature of our software where you can view the overview or look at the details of how that flight is executing. Electromechanical systems. This is getting into more of that realm of the inverter and the motor affect that mechanical system. So we have a lot of customers when they're doing their characterization, looking at things like what's my thrust and what's my vibration. So here's a DC motor during a startup where we're increasing the load and then coming to a steady state operation. And we can see that as this motor speeds up, we get an increase in thrust and our vibration tracks with that thrust. And this is just an example of our software looking at all of those things in parallel. We can even get to a point where if you wanted to zoom in and see the phasing between your current and your vibration, you could do that. If you want to play with your controller to mess with your phasing, you can see those things and have confidence in that time alignment. So you can have a lot of confidence in that time alignment so you can understand the phasing between electrical and mechanical. You can start to understand those complex systems, analyze resonances, and generally come out with a higher quality product. Especially when we start looking at a lot of these structures are thinning materials, they're lightweighting, we're going to narrower wings. We need to be really aware of the vibration our machines are creating. Along those same lines, we can take those measurements from an inverter and we can look at, what is my voltage, what is my current, what is my torque. We can change a control scheme, look at voltage, current, torque. In this example, there's a ton of torque ripple. And then we can do the same kind of color maps that we would do in a noise or vibration setting with this data. So this data is exportable. This data can be used for color maps and understanding, again, that mechanical system. What's the electrical effect on the mechanical system? And this data can be shared throughout simulation, throughout the structure teams, so you can really start to piece everything together. Here's an example of a actuator test where we had a customer who was looking at testing multiple actuators. And they wanted to look at, all right, what is the actuator's performance and how hard can we push it until it fails? What's its response timing? So this customer was measuring the electric power going into both actuators. They were measuring a load cell for the thrust force. They were measuring displacement, acceleration, and thermal. And they're doing that all into our eDrive system. So wide variety of sensors, continuously recording data, all time aligned. And they were really pushing the frequency to see when, their current sensors started failing, when their windings started breaking down, when they lost frequency control. And this really simplifies the setup so you can see all of that data in one location. Fault testing, one of my personal favorites. So talking about pushing a motor to failure. again, not a lot of people share their data with me, so I had to fail a motor on my own. So to do a demonstration of demagnetization, I cooked a rotor and pumped a ton of current at it. And to demonstrate short circuit, I induced the fault in a motor winding. And what we saw was, we were recording data on this motor for both scenarios. This is data from the short circuit test, going through various speeds. And then here we can see we inject the fault, and the motor's behavior gets a lot more sporadic. And we can see voltages dipping. And in this type of scenario, we were operating for quite a long time, and we triggered an event right here. We had a pre-trigger where we recorded, what is this, like 5 seconds of data before and 5 seconds of data after. But you could potentially record for as long as you have hard drive space if you really want to understand what leads up to a fault condition. I injected this, so it was a little more abrupt, but in the circumstance you're running for a long period of time, you likely don't have that luxury. And we can do all the calculations if you want to track or trigger on calculations as well. So here was an example, and I'm showing just some plotted graphs of RMS voltage versus frequency and reactive power versus frequency. And we can see that in my short circuit test, the values are all over the place. In my healthy test, we can follow them quite consistently. And in my demagnetization test, there's definitely an altered value. So if you want to track what leads up to a fault, you can absolutely, do a little machine learning and follow long-term averages to track things like failures. Because while the short circuit's quite dramatic, the more realistic scenario of demagnetization is a lot more subtle. And we can see that in our reactive power. Once we get to a certain frequency, we can see that in this demagnetized case, we have a very subtle shift at a higher frequency. These are things that you can track. These are things that you can trigger on. And in the event you're testing for a very long period of time, we can record data for hours, days, weeks, and again, trigger for events. And here's an example of we were monitoring temperature and THD on a motor. And if you look down here, we have 12 hours per division. So I think this was a 5-day test where we were looking at a motor's THD and triggering when it got above certain levels to understand what was happening to this motor over time. So you absolutely can track things like harmonics, like temperature, for days or weeks if you're really looking for durability type testing. So poll question 2. Chris, if you could throw a poll question 2, that would be greatly appreciated. All right. Now here's a question. Do you guys care about system level? Yes, it's important to my job. Yes, I care, but my division of the organization doesn't. No, I only focus on components, or system is an awful buzzword. And I seem to trend towards the latter while believing the first. Cool. And yeah, I'm glad to hear that it's important for a lot of people's jobs, especially since the majority of you were aerospace folks. So that's excellent. Thank you, guys. All right. So that leads me into Flutter, which honestly, from the physics standpoint, I think is the most interesting thing I'll present here today. So for those of you who don't know what Flutter is, this is a terribly old video. But it demonstrates the point really well, where we're looking at this rotation kind of slowed down, and we can see that the propeller blade is actually kind of oscillating along itself. And you can see that it's really affecting the nacelle and the vibration in the nacelle and ultimately the wing. Now, that was an old jet engine. But with the advent of things like torque ripple and these vibrations being produced by the motor, flutter is becoming a real concern. And I already showed this, but we have this tens of kilohertz voltage and current coming from the inverter. that's getting to this torque. We're creating that torsional vibration. And if we're putting torsional vibration into these propellers, we're going to induce things like whirl flutter. And then that's going to transfer to traditional flutter on the wings. So we really need to start thinking about, how does my inverter, how does my electric machine affect my structure? And this is something that in automotive, I almost never had to think about. And just to back that up, if we look at some data from a motor, and we look at, current in red, torque in black, and vibration in blue, and HBK actually has really awesome torque sensors where you can see torque ripple up to 6 kilohertz. And we just plot the simple FFT. Again, this is from our software. We can see our current, and some of our current harmonics, and then our torque ripple and our vibration really lining up. And this is what we're afraid of for things like whirl flutter. And there are cool things you can do in the controller to actually phase your torque ripple. So if you have multiple motors, they're out of phase with each other and you can cancel it out. It blows my mind. But what we end up with is a trade-off between inverter operation and mechanical implications. And I'm going to go through this quickly because I tried to put too much into this. So thank you guys for hanging on. Higher inductance machine adds weight. So we're trying to reduce the weight of our machines. Line filters, capacitors, inductors add weight. We can't have more weight. Higher switching frequencies add losses, even with the silicon carbide. And active controls add losses, active torque ripple cancellation. So if we look at, minimizing our losses, this might have implications for the structures. So we end up with this range and weight have trade-offs with vibration, have trade-offs with damping. And where this really comes into concern is things like torque ripple. So this is a frequency analysis of torque ripple from a motor. And what we see is that it's got a really dominant frequency domain at 8.3 hertz for this specific motor. And this is one of our software packages that's actually for analyzing structural dynamics. If we start to look at the bending modes of wings on a simple aircraft, we're seeing that these are right in the range of something like 8 or 9 hertz. Fuselage bending, 9 hertz. Vertical fuselage bending, 17.4 hertz. So, first bending, second bending. Torque ripple's right in the range of this, which is kind of a terrifying thing. And again, you need to understand that system. What is my wings vibration? What is my motor's vibration? And are those potentially overlapping? High voltage. So I find this just fascinating. I think this is really, really cool stuff from a system analysis. High voltage. We're seeing voltages push higher and higher. And one of the things you need to consider with any piece of equipment is its CAT rating, its safety rating. So all of our products have really the highest ratings we can get, up to 1000 volt RMS, Cat 4, over voltage category, 1500 volt DC, and quite a few ranges. If you need to go higher than 1.5 kV, we have probes that are, passive safe probes. And if you have to go to really high voltages, we have a whole customs teams and fiber optic isolation, so you can keep people safe and keep yourself safe, and keep the equipment safe and the test safe. And we have a lot of really nice high voltage measurement options. Again, that fiber optic measurement system, measure right next to the measurement, send everything back over fiber optic. If the equipment blows up, everybody will be safe. This is just the epitome of safety, and you have that added benefit of really high electrical noise immunity. So it's a super exciting product. Some references, and I will go through this quickly so we can get to questions. Here's a project we participated in with University of Wisconsin, doing testing for NASA's university-led initiative. The slides will be shared so you can look through this yourself. But we were measuring a really high phase count machine, really high efficiency machine for this valuation. Excellent papers. I got to say, I worked with a lot of these people at the university, and it was really fantastic project. This is an example of a H3X, a startup, using our system. You can see the system here, connected to the motor dynamometer. You can see our software evaluating their machine. Again, really exciting stuff in the aerospace. They're really pushing power density. So understanding the temperature, getting the heat out, and the efficiency is huge for them. I got some links to videos. These are publicly available things. ES Aero, we had a picture earlier. They have some videos where you can see our stuff. We like to think we can cover you from prototype to production, because we record that data, because we have that system level measurement, and because we can allow you to test really quickly. And in closing, we make electric and mechanical simple. You can test fast. You can test lots of channels. You can record data, real-time equations and feedback. And we do have experts and local support who are really here to help. We want to share our knowledge. So thank you guys. And I'm gonna look at some of the questions. I read my own. So please give me a moment.
Great, thanks for the presentation. Yeah, we got quite a bit of questions coming through, so if you could just
Yeah.
go ahead and read them aloud and give us your response, that'd be great. And
Yeah.
for the audience members, if you have any questions, go ahead and click the Q&A button on your screen to submit them.
Yeah. So one person asked a question. Are the motors in the system level test, looking at the motor stability, real motors or just simulation? So for the flight sequence test, the motors are actually quite real, because we want to look at how the motors behave in fault type scenarios. The motors are quite real. The simulation is the flight controller, or sometimes it's the real flight controller, and the simulation is the weather and the dynamics of the propeller. So really nice question, and really measuring all of those motors and all of their glory is quite important to understand the stability of things like the DC network, to understand the fault tolerance, to understand, am I going to be able to put the aircraft down in the event I need to. Okay. Beyond prototype development and certification, what type of testing is required in the manufacturing of E-planes, and how does HBK offer such testers? Thank you for the question. Yeah, so I can speak to the powertrain more than anything. I'm far from an expert outside of powertrain. But with a lot of these machines, we're seeing quite complex magnet arrays, whether that's Hallbach or more traditional IPM or SPM. Looking at if the magnets were magnetized correctly, if everything was put together correctly in the rotor, has a big effect on the quality. So HBK does have testers for looking at the rotor back EMF in some really heavy detail, much more than you might get in a traditional tester. Also looking at the power output and power quality of the inverters is a test we're starting to see, where they'll actually fire up the inverter, make sure it's hitting performance specs, spin up the motor, make sure it's magnetized correctly, and then looking at the efficiency and the power output of the pair. So HBK certainly does supply such testers, and I'd be really happy to discuss that more with you. But evaluating the magnetic assembly and evaluating the total performance output is really the key. In automotive right now, we're seeing a big issue with tolerances and things not passing production. So this is becoming a really relevant topic in making sure these motors are evaluated correctly. Let's see. What is your sense of the E-plane market at this stage? Still early? Are you seeing production units? Yeah, I think Beta just opened their factory like yesterday, and I know Joby has a big factory announced in Ohio. So I think there's a lot of momentum in that direction, but this is technical, so I won't get too far into that. Let's see. How fault diagnosis and mitigation, or how is fault diagnosis and mitigation done for the motor? We're seeing in a lot of these aircraft companies, they have departments devoted to fault handling. So they'll have motor control engineers who are pretty dedicated to analyzing, can I predict if a short circuit fault is coming? Can I predict demagnetization? So a lot of it is done through long durability testing, looking at how to divert current from phases if you think demag is coming, looking at how to operate at a lower performance to reduce thermal. So the mitigation's quite an interesting control problem. But what we're seeing is a lot of people just avoiding single point failures and going to higher phase count machines or more machines. So thank you for that question. I mentioned other avionics buses. What are these other avionics buses? I think we're seeing some trends towards IDDS, and that's the one I keep hearing all the time. I am seeing a lot of the motors and motor controllers still relying on CAN or CAN FD, but the one I was referring to and we're investigating is IDDS. Thank you for that question. Is there a standardized battery voltage defined for all electric aircraft? I certainly wish there was. That would make my job a lot easier. Just like automotive, we're seeing the trend for voltage go higher and higher and higher. So I don't think there's anything standard coming for that. Great question, but unfortunately not a great answer. I think that covers them. So thank you all for attending. Thank you for listening, and I hope to hear from some of you. And thank you, ChargeGV, for having me.
Great. Thanks for the presentation, to everyone who attended and submitted questions. That was a great discussion. It's awesome to hear that the aerospace market is so active in development of electrification. I'll just add one final reminder that you can rewatch this session on our website and share it with your colleagues if they couldn't attend. Thanks for joining us all the way from Tokyo, Mitch. I imagine it's pretty late at night if it's not already tomorrow. So thanks for the presentation from the future.
Yeah, goodbye from the future, and hope to hear from some of you. And Chris, hopefully see you soon. If you
Great.
can send me a hat, I'll take one.
Yes, I will.